Hello and welcome to this section of the Physics 3 tutor. Here we're going to continue working problems related to a wire that's carrying electric current in a magnetic field. And really the same exact principles apply. We're just going to be expanding and doing problems of slightly more complexity, a little more steps, but the main ideas are really all the same. So this problem goes as follows. A wire is 50 centimeters long and it lies along the x-axis. It carries 0.5 amps of current in the positive x direction. A magnetic field in the region here around the wire is 0.0030 teslas in the j direction plus 0.010 teslas in the k direction. What is the force on this wire? So we have everything we need because we learned a minute ago that the force on a wire carrying a current is I L cross B. L is the wire direction. I is the current in the wire, L bar, L vector is the direction of that wire, the length of the wire, and it's crossed with B. And we talked about how we derive that and how it makes sense from all the charges flowing through there. They're all getting pushed, so the wire gets pushed. So in this case, though, we have a vector, an actual vector, and it lies in J and K, which is Y and Z directions for the magnetic field. And we're actually also given a vector for the wire because we're told the wire is 50 centimeters long, so we know the length, and we know it's along the x-axis. So from that information, we should be able to just dive right into the solution because the force on a wire, the magnetic force, is I times the length of the wire crossed with B. Now this just isn't the length, this is the length of the wire, and also it takes into account to the direction of the wire. We cross it with the magnetic field strength there. So let's just write it down. The magnetic field that we were given, is 0.0030 teslas in the j direction plus 0.010 teslas in the k direction. And the wire, we're told, is 50 centimeters long and it's in the x direction. So let's set up, first of all, forget about I, let's find L cross B. L cross B. We're going to find this cross product of these two vectors, and then when we get the answer, we'll multiply by the current that we have, and then we'll get the final answer. So the easiest way to do this is, like I said in the last section when we did a problem like this, you can do it however you want, but I've gotten so used to doing this with determinants that it's very easy for me to just remember. I don't have to even look at a book. You just write I direction, J direction, and K direction. So these are the directions that we have, and we're crossing the wire vector L into the B vector, the magnetic field vector. So the wire vector, it says right here that the wire is 50 centimeters long and it's in the x direction. So it's going to have a component along x. 50 centimeters, of course you don't want to put 50 centimeters down. We don't work in centimeters, we work in meters. So 50 centimeters is 0.5 meters. So we just put 0.5 here. It has no component in the j direction, no component in the k direction. Now this is so crucial. I'm kind of glossing over a little bit, but putting that down and knowing that when a problem tells you that a wire is so long pointed in the x direction, for you to know that that means that L bar is 0.5 along x, 0 along y, 0 along k. For you to make that connection is probably half the problem. So a lot of this stuff isn't hard once you know what it's trying to tell you. The problem is telling you the wire does not exist along j, there's not pointed along k. If I drew a coordinate axis, the wire would be lying purely along x, so that's why we put it here. So this magnetic field does not have any component along x, so we put a 0 in there. But it does have a component along y, 0.003, so we'll just put that there. And it does have a component along k, which is a z direction, 0.010. So we'll just put it there like that. Now we just have to do the technique that I've taught you, how to cross these guys. And what you'll end up with is a vector, which will represent the cross product of these two vectors. So that's what we're going to do now. So what we'll have is L cross B is going to be equal to. You just go component by component. So first let's talk about the I direction. So what we do is we mentally cross out this column and we don't even look at this, and we take kind of the determinant of these two columns that remain. So what you'll have, and I'm not talking about this up here, you cross this out, you basically cross this out, and you take the determinant of these numbers down here is what you're really doing. So what you'll have is, let me put a bracket here to make it clear, 0 times this, 0 times 0.010 minus this direction, 0 times 0.003. Close that off. So the I direction in the end is just going to be 0 because 0 and 0, that's all you have, but show all of your work. So we cross this out, this times this minus this times this, and there you go. Now for the j direction, you have to put a minus sign out front, and that's the only thing you really have to remember when you write the j component down. You have to put a negative sign out in front. And when we do that, we cover up mentally this column, and of course we're covering up these guys here. So we're covering this, and we're taking the cross product of these numbers here. So it's this times this, 0.5 times 0.010, that's this direction, minus this times this, 0 times 0. And writing it all down is very important because it actually will let you get partial credit, which is huge as well if you happen to make a mistake. The k direction, just put plus k direction, open up a bracket here. We're going to cross this out, we're going to cross this out, so this is gone. We're taking the determinant over here, which is this guy right here, so we'll have 0.5 times 0.003 minus this direction, 0 times 0, 0 times 0. Now we're done. Okay, so we finally do the multiplication. So we'll have L cross B is going to be equal to, in the I direction, just to keep it all clear, write 0 in the I direction, because this is 0 minus 0. In the j direction, we have a minus j right here from here, and then inside what we have is this times this minus 0. So when you multiply this times this, you'll get, let's do 0.005. That's the component along j. And then for the k direction, you have plus in the k direction, you have this guy, this multiplied together, minus 0. So when you take this and multiply by this, you'll get 0.0015. 0.0015 in the k direction. So this is really the L cross B vector. There's nothing along x. This is the component along y. This is the component along j. And there you go. So in order to get the final answer, remember all we've done so far is we crossed L into B. But to find the force, we have to have I, the current in that wire, times, which is just a number, times this guy. So what we'll have is, for the force, we'll have the current. The current in this problem is half an amp, so it's 0.5. And then we have to multiply by L cross B. So here we go, 0.005 in the j direction. And then here's a minus sign, don't forget, right here out front. So let me go ahead and open this up, keep this minus sign alive that we have there, plus this guy, 0.0015 in the k direction. Okay, and now we're ready to write the final answer. So FB is equal to, when you take 0.5 and multiply by this guy, you will get negative 0.0025 in the j direction, plus take 0.5 multiplied by this, you'll get 0.00075 in the k direction. Now this is the final answer, and sometimes you don't like to see all these zeros and decimals everywhere, so you can just sort of rewrite the answer if you like, not required. FB is going to be negative 2.5 times 10 to the minus 3, that's in the j direction, plus 0.75 times 10 to the minus 3, and that's in the k direction. And what unit do we have? This is a force, so the unit that we're talking about is newtons. So it's negative 2.5 times 10 to the minus 3 in the j direction, plus 0.75 times 10 to the minus 3 in the k direction. So it's really just a bunch of math, but what you need to know is really two things. When in the problem we were given a wire is 50 centimeters long and it lies along the x-axis, you need to know that when you set your cross product up, that means this is the length along the x direction. There's 0 here and 0 here. You need to know that the magnetic field comes down here, and then you need to know the mechanics of how to cross product it. So we go this way, cross these guys, cover this guy, then cross these guys here, and then cover the third component, cross these guys here, and then at that point it's just simplification. Once you have L cross B, take the result, multiply by the current I, and then you get the guy. Now, you could have just left it alone down here, but you know, it's fine to put a decimal here and call it 2.5 times 10 to the minus 3. Put a decimal here and call it 0.75 times 10 to the minus 3. The unit is newtons because we're talking about force. And also, that's important, earlier, whenever we were given 50 centimeters, for you to realize don't use centimeters, convert it to meters here. So in physics, there's lots of different ways to get in trouble. One of the easiest is if they give you a non-standard unit or a non-base unit in your problem, then if we would have put 50 here, then we would have gotten similar numbers, but the scale would have been wrong, and there would have been absolutely a silly reason to miss points on a test. So make sure and keep an eye out for that. All right, now the next problem is a really great problem because it teaches you a lot about what we're learning about, and also it's a great problem to ask on a test or a quiz, and I've seen it numerous times myself, or variations of it. And so once you understand how this is done, then it'll kind of give you the skills to tackle problems that are similar. So the problem goes like this. A half circle of radius r sits in a magnetic field B, which is perpendicular to the plane of the arc, which carries a current I. What is the magnitude and direction of the force acting on this arc? So you see, there's lots of things that are interesting about this. Number one, it's not a straight wire. Everything we talked about so far has been a straight wire. And then, if you're in a uniform magnetic field with a straight wire, it stands to reason that the force, since the current's going all in the same direction, whatever force is acting on the wire is all going to be pushing the wire the same direction. So it's kind of a simpler idea when you have a single wire that's traveling in one direction. But if you have an arc, then the current is really turning, right, through the wire, because the wire's bent. And so even if the magnetic field is uniform, because the current is not straight, then the force acting on different parts of the wire is going to be different, because the direction of the current is going to be different everywhere in the course of that arc. So that's number one. Number two, there's a lot of little goodies here that you need to really be aware of. So the first thing we need to do, I think, is just draw a quick picture to kind of let you know what we're looking at. And then basically what we're doing is deriving something. There's no numbers in this problem. We're deriving what the force on this arc is. So let's go ahead and take it one step at a time and show you how to pull off a derivation like this. Because like I say, you see it in tests all the time. So we have to pick some way to draw this thing. So what we're going to do is, this is a magnetic field. It's coming out of the board. It's coming from the board to you. So that's visualization of the magnetic field. And let me draw one more little layer here, because I'm going to draw a nice big arc so we can have lots and lots of room. It's uniform. That's what I'm trying to say by the spaced out dots. All right. Now inside of this magnetic field, which is coming out of the board from me to you, there is an arc, which is a wire, really. And so what we have is it's coming up, more or less like this, and coming down like this. Now it says in the problem it's a half circle, so that's why I drew it as a half circle. Other variations, I'm drawing a half circle. On your test, you might have a quarter of a circle, which would be this much, and you have to calculate the force, or something like that. Or maybe a full circle. Your professor might give you a full circle. So all of those variations are all going to be similar to what we're doing here. It's slight variations. Make sure you understand what we're talking about in this case. So what we have here, obviously this is physics class. It's not real life. So we're saying that there's a current in this guy, and this current, let's say, is going this direction, down like this. So the current's going up the arc and down. Now, of course, in real life, you have to have it connected to a battery and a circuit and all of that. But just kind of pretend that this is a perfect wire that has a current going through it. And don't worry yourself about where the battery is, where the rest of the wire is, and all that. All we're concerned about is this portion of it. All right. Now, this arc is a circular, semicircular, half circle arc. So it does have a nice radius, which is the same everywhere. And this is a radius r. That's going to come in handy at some point. And we're reminded, here in the beginning, we start thinking about this. We don't know really what to do. But we do know that originally we were given that the force on any wire is I times L cross with B. Now we know what the magnetic field is, and we know what the current I is. We have it labeled anyway. But this L is a little bit weird than what we've had before, because before L was taken to be, since it was a straight wire, L was the length of the wire, and it was pointing in the vector L was pointing in the direction of the wire, whichever direction it's lying. But in this case, the wire direction is changing the whole time, so this is a little bit different. What we are I didn't tell you in the basic lecture of the class, but when you have something that's not straight, this formulation is not very helpful, because L is not just a straight wire, because it's curved. So what we do is, and you'll see this happen like all the time in physics problems really, is when you have a curved, when you have a generalized equation like this, but you have a curved path you're trying to apply it on, what you'll do is zoom in real tight on one little spot, like a microscope, so that you get so close that it's like locally really straight, like you can almost think of it as a straight thing. And what you would then call it is, instead of L, you would say this little vector here, which is tangent to this point right here. We're getting into calculus a little bit. You would say that this is, instead of L, it's DL vector. So in other words, the length of this arrow is kind of like representing the line tangent to this point right here. And if you could get a microscope and zoom in, then DL is the little differential length L right here at this point. Now, of course, at this point, there's another DL. At this point, there's another DL. At this point, there's another DL. Here, everywhere you look, there's little tiny DLs if you get a microscope. So what we're going to end up doing is looking at the force generated at that point, at this exact moment right there, due to that tiny little segment of the arc of wire and the magnetic field, and it's going to generate a tiny little force, F. We're going to call it dF in a minute. And then what we're going to do is integrate, using calculus, around the circle, right, and add up all the little dFs. Because don't forget, that's what calculus is. That's all integration is, right? You know, when you learn integration back in Calculus 1 and Calculus 2, you're taught that it's the area under the curve, and that's great because it's physical and you can wrap your brain around it. But reality, usually when you're applying an integral, you're not thinking about area. We're not thinking about area here, right? But really what you can think about if you conceptualize an integral is a great way to add up an infinite number of tiny little things. That's what integration really does. So in this case, we're going to look at what little tiny little force is right here due to this tiny little segment of wire, right, in this field. And then we're going to integrate, which is going to add up all the contributions to all the little tiny forces due to all the little tiny segments along this arc. And we're going to get a number when we do the integration. That's going to be the total answer. That is what integration does. So you'll see this theme over and over in calculus when you get farther and farther. When you derive something, you'll zoom in on a tiny part, write an equation for it, and then integrate it over the whole thing using calculus. Bam, there you go. That's how you get your answer. So if this is DL, which is just a tiny little segment of wire here right at this point, which we're going to pretend is straight because we're looking at it so tiny zoomed in there, then if B is coming out of the board, and we know that the force is IL cross B, then if we cross L into B like this, cross L into B, then the force is going to be going this way. So in reality, the force is actually going something like this. And we're going to call this force dF. Because this force right here, this little vector arrow that I'm drawing here, is the force at this point due to a teeny tiny little differential segment of this arc. And it's going to point towards the center of my circle. Right? Now, I want you to use your imagination a little bit. If we walk around this arc, if we go here, for instance, then DL is going to be tangent to this point, and DF is going to point to the center. If we walk around here, the differential L DL is going to be tangent to the line, and the force is going to be pointing to the center because we cross product it everywhere you look. Everywhere you try to go around this arc, and I can't change and contort my arm as I go around, but if you keep doing the cross product at every little point, the force is always going to point to the center of this semicircular arc. So I'm only going to draw it in one place, but keep in mind that we're going to walk around and this force is always going to be pointed like that. All right, so since now we're not talking about lengths of wire and forces, we're talking about DL's, tiny little lengths of wire, and DF's, tiny little forces, then really what we need to do is write another equation. This is the equation we're really going to use, which is really similar. DF, the differential force F, at the teeny tiny little segment, is going to be equal to I, which is the current, that's not going to change, times DL crossed with B. So the only difference between this equation and this one is we have a DF instead of an F and a DL instead of an L. The reason that I didn't explain it to you earlier in the class is because it really doesn't make sense to really learn about this until you have a problem where you have a curved arc of something, which is going to require you to integrate as you go around the boundary. So you basically use this when you have a straight wire, and you use this anytime you don't. When you have a curve, maybe you have a figure 8 wire, or you have a crazy smiley face wire, or something that's not straight, you'll use this. It's the generalized form. So this is the tiny little force at this point. We're going to use this guy and integrate around. Now the only other thing I want to say is, if you think about it, this force at this point, it's pointing to the center of the circle. Now this is a vector force like any other force. We can decompose it. So this vector can be decomposed into a vertical vector pointed straight down, and also a horizontal vector pointed this direction. This is basically just a vector sum of this oblique vector right here. So when you think about it, I'll label it a little bit better here in just a second, but when you think about it for a second, because you know a lot of times, especially when you have an arc in physics, symmetry is very important to simplify your problem. If I look at this guy right here, I've got basically a force going to the right and a force going down. If I go to the other side and go this way, Then I'm going to have a force acting down, and I'm going to have a force acting to the center, because we already said the force acting on this point of the wire is always going to point to the center of the circle. So if this is my force, I'm going to decompose that into a component this direction and a component down. So as you can see, as you walk everywhere along this half of the circle, you're going to have a component, little components going to the right. These guys right here. And then when you get to the other side, you're going to have little components going to the left. So everywhere you have a little component going to the right, you're going to have an equivalent point over here that's going to have a component that's going to cancel out, point in the other direction. So that's very, very important for you to understand that symmetry, because really we don't care about df oblique vector. Really all we care about to solve this problem is this one pointed down right here. And this guy really is df times the sine of theta. And theta is defined to be, let me draw this guy right here, this angle here, theta, because that's going to be the same as this angle here, theta, inside there. So if I take this vector, which is the purple one here, and I take the sine of it, I'm going to get this component pointed down. This is the component that I really want to add up as I walk around this circle, because everywhere I'm at, no matter if I'm here, I'm going to have a downward component. If I'm here, I'm going to have a downward component. If I'm here, I'm going to have a downward component. When I get up here, I'm going to have a very large downward component. When I get on this side, I'm going to have a downward component. When I get on this side, downward component. Everywhere I go, I'm going to have a downward component, which of the force. So when you look at this guy, the force that this magnetic field is going to exert on it is going to be pushing the entire arc down, because everywhere I look on this arc, I'm going to have a downward component of this force. But if you look at the left to right, the horizontal force, they cancel. On the left-hand side, they're pointed this way, and on the other side, they're pointed this way. So we really don't care about this. Really what we want to add up is this. So really, without even doing any math at all, just by doing a nice drawing and thinking about symmetry, we know that this arc is going to be pushed downward. And the left and right forces are going to basically cancel out. We're not going to be able to see them, so we don't care about them. They disappear. This goes back to lots of other problems we did with Gauss's law and other stuff earlier. We had symmetry, we take advantage of it. So that's what we're doing here. All right, I promise you, we're almost to the end of this problem. Once you know how to set it up, the problem is like that. It's really simple, but setting it up does take some time. So what we care about is this force times the sine of this angle. That's what we're going to add up as we walk around. So the total force on this wire is going to be the integral of df sine of theta. And what we need to do is figure out how to transform this integral so that as we integrate, we're going to integrate from like 0, let's say, all the way to pi. So we're going to integrate over an angle, 0 to pi, and everywhere we walk around, we're going to be adding up df times sine theta. So when theta is here, when theta is here, when theta is here, we're going to walk around everywhere we have theta. We're going to take the force that we get, we're going to multiply by sine theta. That's the downward component. The integral adds it up. We walk to the next place, the integral adds that component. We walk to the next place, the integral adds that component. We keep adding and adding and adding and adding, and we're going to get a total force. That's what we're doing. All right, so we're finally ready to do it. So what we're going to have here, the force, is going to be equal to the integral. df, we already said it was I dl times, or cross with b, but since we've already done the vector components, since we know that the magnetic field's coming out of the board, since we know that it's perpendicular to this arc, because the arc is lying in a plane perpendicular to that, then what we're really going to have is, this is going to be, this df really, the magnitude of the force really is what we care about, is going to be I times dl times b. This is a multiplication, I dlb. Let me put some parentheses here. In other words, the magnitude of the force is going to be I dlb, center seeking like this. The reason we don't put a sine theta here is because we know that the arc here is perpendicular to the magnetic field. So it's really I dlb sine of phi, which is the angle between the arc and the magnetic field. But the arc is lying in a plane totally perpendicular to this guy, so it's always going to be 90 degrees, so the sine is always going to be 1. So the magnitude of the center-seeking force, no matter where we look, is I dlb. So what we do is we stick that in there. This is what we're going to be adding up. We're going to put it in like this. Let me just put the b in front because it'll be a little easier. IB, and then we'll have dl, okay? And then, let me put a little guy here, sine of theta. All right, now let me get through the integration and get the answer, and then I promise we'll walk back through it and make sure everybody understands. This sine of theta is because we're chopping our force and only taking the sine of it because that's all we're adding up as we go around. So this guy, let's go ahead and transform it. We're going to integrate from 0 to pi, so we're going to integrate over an angle. I, B, and now we have to put something in for dl. Obviously we have a theta here. Okay, that's cool. Magnetic field is constant. We're going to pull that out later. This current is constant. We're going to pull that out later. But this dl we need to think about a little bit because we can't integrate over just a dl. We have to somehow convert it to an angle. Now go back to our drawing and look here. If you remember back from basic geometry or basic physics, what you have here is an arc with a radius r. So when you have something like this, then what you can say, you can calculate an arc length along the path here. Arc length, usually it's called S, it's called arc length, is equal to r times the angle theta. So in other words, if you want to know what the length of the arc here is along this path here, you just take the radius and multiply by the angle in radians that you're trying to sweep out, and that's going to give you the length along this guy right here. That's the arc length. All right, and since that's what we're really doing here, we're integrating over this path. So for dl, which is the length along this path, we're going to put r, let me go ahead and, I can use this color, r times d theta. And let me go ahead and put sine theta. This is really a crucial step. This is really the step that enables everything. You're trying to find out what dl is, but it's changing as you go along the whole way here. So what you do is you look at a little segment dl and you say, okay, this little dl is going to be equal to the radius times a little differential angle d theta. That's going to be what I'm going to call dl equal to, and that comes straight from the arc length formula. So now this is constant, the radius of the circle is all constant, so I can pull all of that out. So now what I can do is I can say the force is going to equal, all of these are constant, I is a constant, that's the current, magnetic field's constant, the radius of this circle is constant, the integral is between 0 and pi, and I'm just going to rearrange this to make it easy. Sine theta d theta. Now this is an integral you know how to solve. These are all constants. This is just an integral of a trig function. So let's go write it down. So f is going to be equal to I, B, R, integral 0 pi sine theta d theta. Okay, so what's the integral of sine? Integral of sine is negative cosine. So we'll have f is equal to I, B, R, negative cosine theta, right? That's the integral, evaluated from 0 to pi. So what we'll have is I, B, R, and then we're just basically in calculus mode here. What we'll have here is, we'll go ahead and pull, we'll do it like this. So negative cosine of pi minus negative cosine of 0. Negative cosine of the top minus negative cosine of the bottom. And so, getting close to the end result here, cosine of pi, when you think about it, is negative 1. Cosine of 0, when you think about it, is positive 1. So f is equal to I, B, R. Negative times negative gives me positive 1. Negative times negative here is plus. This guy we said was 1. So the force on this arc is 2, because 1 plus 1 is 2, times I, times the magnetic field strength, times the radius of the circle. 2IBR. That is the force acting on the entire arc after we integrate around the whole thing. What direction is it going? We already said the force is down, which is the negative y direction, pointing down. If you think of y being positive up. So this is the answer, 2IBR. Now let me go through it again because there was quite a bit of stuff here. But when you step back and just look at the whole thing, there's not many steps. I've got maybe 3 steps here. I even rewrote a step here. Maybe 6 or 7, 8 steps total in this entire problem. But physics is deceptively simple like that. You're like, oh, this is a few steps, no problem. The problem is doing this, figuring out what's legal, what makes sense. And so this is a great problem for that, because what you have here is a situation where we have an equation that is governed by a straight wire, and this is not a straight wire. So I'm telling you that this is the equation that you'll use in these cases. So instead of IL cross B, you have I times DL, differential segment, cross with B. This, when you do this stuff, is going to give you a differential F, a small little force F, right here. I've drawn it on the board. That's the force at that specific point, and we want to walk around the circle and integrate and add up those forces. But what we figure out pretty early on is that because of the symmetry, the horizontal forces cancel out. So we don't even care about those. We're not even going to integrate that. And what we also know is that the vertical forces do not cancel. You can see that from the fact that everywhere we go, we're going to have a vertical component. So really what we want to add up is df times sine of whatever angle we have here. And I've drawn the angle here. Now what we're going to do is go through this whole problem and understand it. But before we do so, I want to make one very small correction that I'm noticing here. It doesn't change the logic of anything. This angle here, theta, that I've defined is correct. But really it's the same as this one right here. So I'm going to put this here, and I'm going to call this angle theta, which is this angle of this triangle. So this vertical horizontal side, you can see now from the way I've drawn it correctly now, the sine of it, df times the sine, is going to project it vertically, which is what we care about here. So I was wrong to show this angle being up here at the top. It's really down here in this corner. It's just a labeling thing, but all the logic is essentially correct. So what we've noticed here is that they have symmetry in this guy. We have started with an equation that we're given for a straight wire, and we have sort of a differential form of it when the wire is curved. So every little segment dl, when you cross it with the magnetic field, is going to produce a df vector pointed towards the center, but we notice from symmetry that everywhere we go, the horizontal components of these guys would cancel. On the left-hand side, they're going to fight with the right-hand side, so really the entire arc is being pushed along the sides like this, but that's not going to tend to move the arc anywhere. They're going to just fight with each other and cancel out. But the vertical components, the up and down components, this guy right here, the df sine theta, does not cancel, and they are additive. So that's really what we care about, since we're trying to find out what's the net force on this wire. All right, so the next thing we do is we figure out, okay, so this is the equation we have, I dl cross B. We know what direction the force is going to ultimately point, so we say the magnitude of the little tiny force df, once we take, once we really look at it, is going to be I times dl times B. That's the magnitude. Usually you'll have I dlb times the sine of the angle between the wire and the magnetic field. But since the wire is lying in a plane, literally the magnetic field is coming out of the board. So the magnetic field is always perpendicular to this wire. So you don't need a sine phi here, because it's just going to be sine of 90 degrees always, so you're going to get 1. So this really is the magnitude of this arrow everywhere we go around the circle. So what we want to do is take this force that we have here, that's everywhere around the circle, multiply by sine theta. That's going to give us the vertical component of it everywhere, and we want to add that up as we go around the circle. So that's why we introduce a sine of theta here. It's because we're taking that df, we're multiplying by sine of theta. That's the vertical component. We need to add it up. So df is given by what we have here, I, B, dl, sine theta we've introduced. I and B are here, that's fine. Now we have to do something with dl to turn it into an angle so that we can actually do this integration over an angle. So we go back up here and we say, all right, dl, a little differential length along the arc, is going to be equal to r times some d theta, some small incremental theta. That comes straight from an arc length formula. So S is r theta. So in this case, dl is r times d theta. R is a constant everywhere. So it's just a mechanism of transforming this arc into an angle, basically. And you see that a lot in these integrals that do this sort of thing. So I, B, and R are constants. They come out of the integral sign, and you're integrating sine theta d theta from 0 to pi because you're going around a half circle. And then at that point it becomes calculus. The integral of sine's negative cosine, you plug in the limits of integration, simplify everything, this is the answer. So if you actually built a semicircular arc, if you put a current through it that had I amperes, whatever I was, if you put a magnetic field coming up through the bottom of that arc perpendicular to it with so many Teslas, and the radius of that arc was so many meters in here, then the force in newtons would be the product of all of these little terms, and that would be pushing that arc down just like it's in our drawing here. There would be no side-to-side net force. There would just be trying to scoot that arc down with so many newtons in the negative y direction, and that's how that basically works. So that's all I have for this section. Those are two really good problems that are practical that you're guaranteed to see at some point in the future. And I recommend that you watch these as many times as you need. This last one has not so many numbers in it, but conceptually it's really good because as you learn about doing the more advanced physics, a lot of times these derivations, either you get them or you gloss over them. You can gloss over them up to a certain point, but getting them and understanding them really helps. So I tried to give you an example here of a case when we do a derivation like that. You might see it on your test, and even if you don't, it'll help you understand all the other topics that are in your class and that you're being taught. So I'm Jason with MathTutorDVD.com. Watch this as many times as you need to understand it, and follow me on and we'll work some other topics dealing with magnetic fields and forces, and eventually here in a minute we're going to talk about a current loop. So instead of an arc, we're going to have a loop of current, and that's going to be the basis of an electric motor.